the ultimate cosmic enigma. Imagine a place in space where gravity is so strong that nothing, not even light, can escape. This is the essence of a black hole, a region in space where the gravitational pull is so intense that it warps the very fabric of the universe. Black holes are formed when massive stars collapse under their own gravity at the end of their life cycles. This collapse results in an incredibly dense core, where the gravitational forces become overwhelmingly powerful. It's an enormous amount of matter packed into an infinitesimally small space. This extreme concentration of mass warps the fabric of space and time, creating a region from which nothing can escape. This warping of space-time is so severe that it creates a boundary known as the event horizon. Once something crosses this boundary, it is pulled inexorably towards the center of the black hole. Once something crosses the event horizon, its fate is sealed. It will be drawn into the singularity, a point of infinite density at the very heart of the black hole. Think of the event horizon as a cosmic point of no return. Light itself cannot escape. This makes black holes invisible to the naked eye, detectable only by their effects on nearby matter and light. Black holes push the boundaries of our knowledge. They challenge our understanding of physics and the nature of reality itself. Scientists use advanced telescopes and instruments to study these mysterious objects, hoping to unlock their secrets. They hold secrets about the very structure of the universe. By studying black holes, we can learn more about the origins of the cosmos, the behavior of matter and energy under extreme conditions, and the fundamental laws that govern our universe. To understand how a black hole is born, we must first look to the stars. These celestial bodies are not just points of light in the night sky. They are the universe's brilliant nuclear forges, where the elements that make up everything we know are created. Stars are dynamic, evolving celestial bodies. They go through various stages of life, from their birth in nebulae to their eventual demise, which can be as spectacular as a supernova explosion. A star is a gigantic, glowing ball of gas, primarily hydrogen and helium. These gases are pulled together by gravity, creating immense pressure and heat in the star's core. Gravity tries to crush the star inward. This force is so strong that it can bend space and time, creating gravitational waves that ripple through the cosmos. Nuclear fusion in the core prevents collapse. This process involves hydrogen atoms fusing together to form helium, releasing a tremendous amount of energy in the form of light and heat. Hydrogen atoms fuse to form helium, releasing energy. This energy radiates outward, balancing the inward pull of gravity and keeping the star stable. This energy counteracts gravity, keeping the star stable. The delicate balance between gravity and nuclear fusion is what allows a star to shine for millions or even billions of years. Stars are born from vast clouds of gas and dust called nebulae. These nebulae are the nurseries of stars, where the conditions are just right for new stars to form. A disturbance causes a denser region to contract, igniting nuclear fusion. This disturbance could be a shock wave from a nearby supernova, or the gravitational pull of a passing star. High-mass stars live fast and die young, setting the stage for black holes. When these massive stars exhaust their nuclear fuel, they can no longer support themselves against gravity and collapse, often resulting in a supernova explosion. The remnants of these explosions can form black holes, the mysterious and powerful objects that continue to intrigue scientists and astronomers alike. Once a star ignites nuclear fusion, it marks the beginning of a new phase in its life. This process is the heart of a star's energy production, where hydrogen atoms are fused together to form helium, releasing a tremendous amount of energy in the form of light and heat. This energy is what makes stars shine so brightly in the night sky. It enters the main sequence, a stable period in a star's life where it spends the majority of its existence. During this phase, the star maintains a delicate balance between the gravitational forces pulling inward and the pressure from nuclear fusion pushing outward. The star is in equilibrium, converting hydrogen into helium in its core. This process can last for millions to billions of years, depending on the star's mass. The larger the star, the shorter its main sequence phase. Our Sun is currently a main sequence star, steadily burning hydrogen in its core. It has been in this phase for about 4.6 billion years, and is expected to remain so for another 5 billion years. Massive stars burn through their hydrogen fuel quickly due to their higher core temperatures and pressures. These stars have much shorter lifespans compared to smaller stars like our Sun. As a star exhausts its hydrogen, it begins to undergo significant changes. The core, now deprived of its primary fuel source, starts to contract under the force of gravity. Its core contracts and heats up, reaching temperatures high enough to ignite the fusion of helium into heavier elements. This marks the beginning of the next phase in the star's life cycle. For stars like our Sun, this ignites helium fusion, causing the outer layers to expand and the star to become a red giant. This phase is characterized by a dramatic increase in size and a cooler surface temperature, giving the star a reddish appearance. Very massive stars continue fusing heavier elements in their cores, progressing through a series of stages where each new element is fused into an even heavier one. This process continues until iron is formed. Each stage of fusion happens faster than the previous one, as the star's core becomes increasingly hotter and denser. The fusion of heavier elements releases less energy, leading to shorter and more intense phases. This rapid progression eventually leads to the formation of an iron core. Iron fusion does not produce energy, and thus, the star can no longer sustain the outward pressure needed to counteract gravity. The formation of an iron core marks a critical turning point. Without energy generation, the core becomes unstable and starts to collapse under its own gravity. The core starts to collapse rapidly, leading to a dramatic increase in temperature and pressure. This catastrophic event sets the stage for the star's final moments. This leads to the star's dramatic end, often resulting in a spectacular explosion known as a supernova. The remnants of the star can form neutron stars, black holes, or be dispersed into space, contributing to the formation of new stars and planets. The journey of a massive star through fusion stages is like climbing a ladder of elements. Each fusion process releases energy, supporting the star against gravity. Iron fusion consumes energy, shutting down the core's furnace. The iron core is incredibly dense. Without fusion, gravity overwhelms the core. The star is on the brink of catastrophic collapse. The collapse is rapid and violent. The core collapses at incredible speeds. This triggers a supernova explosion. Protons and electrons form neutrons, releasing neutrinos. The core becomes a dense ball of neutrons. The infalling material bounces off, creating a powerful shockwave. The supernova, a star's spectacular demise. The core implodes, forming a proto-neutron star. The outer layers rebound, creating a shockwave. This shockwave is the heart of the supernova explosion. Neutrinos re-energize the shockwave. The shockwave blasts through the star's layers. The supernova can outshine an entire galaxy. The explosion enriches the universe with heavy elements. These elements are essential for planets and life. We are made of stardust from ancient stars. Supernovae seed the cosmos with ingredients for future stars and planets. The birth of a stellar black hole, gravity's final victory. After the supernova, the core's fate depends on its mass. A light core becomes a neutron star. A massive core collapses into a black hole. The core's density becomes infinite at a singularity. The event horizon forms, a boundary of no return. The core becomes a stellar mass black hole. Gravity triumphs over all other forces. The black hole is invisible, detectable only by its gravitational influence. It signifies the ultimate triumph of gravity. Stellar mass black holes, the common cosmic monsters, formed from the death of massive stars. If the core retains more than 3 solar masses, it collapses into a black hole. These black holes have masses ranging from a few to tens of solar masses. Their event horizons are surprisingly small. Despite their size, their gravitational influence is profound. Detecting them involves observing their effects on nearby stars. X-rays from accretion disks also indicate their presence. Our Milky Way contains millions of these black holes. Binary systems provide opportunities to study them. Cosmic titans, supermassive and elusive intermediate black holes. Supermassive black holes reside at galaxy centers, Sagittarius. A** has a mass of about 4 million suns. Their formation is still a cosmic puzzle. They may have started as smaller seed black holes. These seeds grew by accreting gas and merging with other black holes. Intermediate mass black holes range from 100 to a few 100,000 solar masses. Evidence for IMBHs is elusive. They may represent the seeds of supermassive black holes. Understanding black hole masses is crucial for galaxy formation. Supermassive black holes regulate galaxy growth. Unveiling the universe: why black holes matter to us. Black holes test the limits of our physical theories. They are natural laboratories for general relativity. Black holes play a critical role in cosmic evolution. Supernovae disperse heavy elements essential for life. Supermassive black holes influence galaxy formation. Studying black holes leads to profound theoretical insights. Observing black hole mergers confirms general relativity. The quest to understand black holes drives human curiosity. They guide us towards a deeper understanding of the universe.